Good evening, everyone. My name is Shishir Patil, and I'm currently a first-year PhD student at UC Berkeley. Today, I'll be presenting GesturePod. This is the work done at Microsoft Research India, where I worked for 2 years as a research fellow and where my collaborators are from. All right. So, imagine I'm a visually impaired person in a busy street with a cane in one hand and the bag in the other. Right? Both of my hands are occupied. I have just booked a cab, and now the driver is trying to contact me. How do I access my phone when both of my hands are occupied and the phone is in your pocket? Right? You could think of many such scenarios where both the user's hands are occupied and it becomes difficult to access the phone. For example, in this scenario, keeping the cane or the bag in the middle of a busy street is not the wisest thing to do. Right? So, one way to improve access to the phone when both of your hands are occupied is to use voice commands. If a visually impaired person has a earplug in one of his ears, then he could use voice commands to interact with his phone. When we did user studies and we spoke to users, we realized that there is not widespread adoption of this technique. So why is that the case? Firstly, because voice commands are not accurate in all settings, for example, in noisy environments. It's hard to imagine walking out in New Orleans, like on Halloween night, and then expecting to interact with your phone using voice commands, right? Similarly, voice commands are not available for all languages. There are many Indian languages for which there is no good support. And third, most importantly, is the privacy concern. Especially for people with visual impairment, they would prefer not to interact with voice because they're not completely aware of who's in their environment. It's hard to figure that out. People have also tried to use wearables like smartphones to interact with their phones, except that when you have both of your hands occupied, it becomes hard to now use any of these techniques either, so that doesn't hold in this setting. Considering that visually impaired people usually use wide cane, there has been prior work on augmenting the cane with buttons or touchpad. However, people do not adopt this widely because they don't like to change their grip. Every time you add something to the handle, people have to change how they use their grip. For example, using this touchpad. As Shaheer points out from Seeing AI, I'm not a fan of devices which put the electronics in the cane handle, making it heavy and bulky. So, faced with this problem, here's our idea. What if we perform gestures on the cane to control the phone? For example, wouldn't it be powerful to navigate the notifications forward by doing the right twist and navigate backward by doing the left twist? By simple and natural perform gestures on the cane, can you now augment the cane and interact with your phone? So, we set out to build this system. From our user studies, we learned that for a wider adoption for any device we build, there are 4 challenges we need to address. First, lightweight. The device that we build has to be lightweight, else it may break the balance of the cane. And second, like any regular commodity electronic hardware, the battery has to last at least a day for it to be practical in the real world. And third, considering a target audience is the global south, it must be low cost as well. And finally, the gesture recognition system that we built must be robust across users, environments, floorings, so on and so forth. So to reduce power consumption and keep the cost low, we decided to use commercially off-the-shelf sensors. This is an IMU that we use from Bosch. Here's a Cortex M0 class microcontroller, a BLE module that communicates any gesture we detect to the phone, and a LiPo battery that powers the entire subsystem. To the left is a GesturePod, and to the right is the disassembled version of the GesturePod, including the mechanical components and the electronic subassembly as well. So, were we able to achieve what we wanted? First, yes, the form factor and the weight, as I will show you, is pretty small. It weighs less than 50 grams. It lasts more than a day, and it costs less than $10. Needless to say, the weight and the cost can be reduced further as well. Now, with such a low-end device, the question is, how do you address the gesture recognition challenge? How do you robustly categorize these gestures in this low-resource scenario? So here are the 5 gestures that we came up with. The motivation of this is well described in the paper. Let me just now show you how to perform the gestures. So this is a wide cane and this is a GesturePod. As you can see, it's pretty small form factor, and if you can't see, that means it's really small. So here are our 5 gestures. The first is double tap, when you just tap the cane twice. The next is you have a right twist, you have a left twist, and then you have a twirl, and then you have a double swipe. We intentionally kept the gestures to be very subtle and intuitive because visually impaired people would not like to gather the attention, and that's why we don't have any Harry Potter kind of gesture or something like that. Okay. So now that we have these gestures, how do we classify them? Like I mentioned, it's very intuitive to perform. It makes it extremely complicated to detect. For example, if you're climbing up a stairs, there's an inherent double tap that's involved. So first is we tried to compute the gestures by streaming all the data to your phone or cloud. But then we realized that you would be draining out your battery in a few hours by doing this to sustain the high data rate that we have. Second is that we try to classify on the microcontroller using rule-based techniques. But like I mentioned, since the gestures are so similar to the natural way how you interact with the cane, it's hard to have classical rule-based techniques that generalizes across users, across handedness, right-handedness or left-handedness, and across different floorings as well. It could be a carpet flooring or tarmac or even marble flooring, right? So we had to come up with a machine learning-based approach to robustly recognize these gestures. Here's a workflow for a classical ML system. You first collect the data, you featureize it, you collect more training data, you use a classical algorithm, and then you do a final inference, right? In our setting, we had to go and innovate on each of these axes. First is collecting data. We built custom tools and sets that help you manually curate data. What this means is that if you're a visually impaired person, you can go ahead and train a new gesture for yourself. It shouldn't take more than 10 minutes. Featureization. Traditionally, people used fast Fourier transforms and other sequences to classify time series data, but since we're using such a small microcontroller to save power, you can't use FFT or any of the complex techniques to featureize your data. So we have a bunch of custom features that can also work in an online fashion. Training data. So I did mention how we collect data in the first instance. This includes data for double tap and all your gestures. But if you were to just collect the training data, then your system would keep firing every single time. We realized that what you really have to do is go collect lots of negative examples. This includes partial gestures, like what happens if there's a single tap, a half twist, or a part of a signature of some positive. Second, when visually impaired person uses this cane in the real world, it's quite likely that he may hit across flower pots or gates. Now, how do you make it robust to these settings as well? And third, people tend to use the cane at different angles. So now how do you make it robust to that as well? Finally, we also have some techniques when you try to reduce the number of data you have just to make it more computationally tractable. So once you have your training data, which includes the positives and the negatives, you next have to come up with a classification algorithm. We decided to rely on Proton, which is a multi-class classifier published at ICML from our team, which organically fits into our low resource setting. Proton was meant to work in a low resource setting of a few kilobytes of RAM. And finally, and most importantly, now you have to carefully orchestrate this entire pipeline that you have for inference on the microcontroller, which is, again, like I point out, very low resource. Okay, so we had the form factor, we had the battery, we had the cost, and now we also have a robust gesture recognition system. I would also like to point out that the data set we have collected has been open sourced under the MIT license. You can access it here at ak.ms/GesturePod. And this has already resulted to multiple publications which use this as a benchmark and try to build upon this. All right, I should also point out that we did build an Android app on the phone. So our Android app is a simple state machine, and based on any gesture that you perform on the cane, we just communicate the gesture over Bluetooth low energy to your phone, where corresponding state transitions happen. That's pretty simple. Having built the system, we next wanted to evaluate the robustness of our gesture recognition model. So we conducted an in-lab user study. We recruited 12 users from NGOs who are not affiliated with MSR, and we wanted to evaluate two questions. The first is how robust is the gesture recognition system across users, environments, handedness. And we found that the GesturePod performs amazingly well with 92% gesture recognition accuracy. The next question we wanted to ask is, what is the impact of GesturePod on the time taken to perform day-to-day tasks? So look at this graph. On the x-axis, you have simple tasks like receiving a phone call, dialing back on a missed call, or getting to know what your location is, and on the y-axis, you have your speed up. Now, if your speed up is 1, that means that the time you take to perform a task from your GesturePod is the same as the time you would take to perform if you just had your phone. Your phone versus your phone with the GesturePod which talks to your phone. So 1 means you're doing equal, anything better than 1, you're doing better. And here are results. As you can see, GesturePod improves the time taken to complete tasks significantly, anywhere between 3x to 10x, when both hands of the users are occupied. You can see that we do exceedingly well for location, where we are faster by about 10x, which is simply because we enable a one-shot technique to know your location, versus a series of steps you have to follow to find your location on your phone. Surprisingly, we found that using GesturePod, you can improve the time taken to perform particular tasks even when your hands are unoccupied, as in only one of your hand has your cane and the other hand is free. Even then, we improve the time taken to perform particular tasks as listed here. So we had amazing results from the in-lab study. In fact, some users came and asked us, when can we buy this? So motivated by this, we decided to conduct, as a summary, we improve the time taken. So motivated by this, we also decided to conduct a round of in-wild studies. We recruited 3 participants, again, none of them affiliated with Microsoft Research, and we handed the GesturePod to the 3 users and asked them to interact with their phone, either using the GesturePod or using just their phone based on what they deem fit wherever they find themselves in. So here we plot the days on the x-axis and the number of gestures that we detected on the y-axis. Note that the y-axis is in log scale. And here's how our 3 users used our GesturePod. All 3 users regularly used GesturePod across the 15 days, even after the novelty wore out after the first 2 days. An interesting observation is that P3 used a GesturePod more than 1,000 times on a few days. This was not what we expected. So when we inquired, why is this the case, post the study, he told us that he's a teacher, he's a mobility teacher, and on some days he let his students get a feel for the GesturePod as well. So that explains why you get more than 1,000 times on a few days. But as you can see, on an average, people continue to use the GesturePod throughout the 15 days, and this was quite motivating for us. Feedback from users. So post the study, we also did a qualitative feedback session, and here's what all 3 users gave us positive feedback, and we present some responses. So P2 says, when I was traveling by metro, holding the cane in one hand and the railing in the other hand, I'm getting calls. Before it was not possible to answer them. Now I can talk using the cane. So you have your earpiece plugged in, and based on gestures on the cane, you can now start or end the conversation on your phone. P3 had to add, earlier I had to take my phone from my pocket and stand somewhere to pick up a call, but now I can answer it while walking. This was quite interesting for us because we did not design the gestures to be used while you're in motion. It was meant to be you stand at a particular place and do it, but our users figured out that they could perform the gestures while in motion as well, while walking. And P1 had to add in footpaths, even without any luggage in our hand, we have to stop and then remove the phone from our pockets and then note the time. This makes people behind us stop. Also, this is very long. With cane, we can know the time immediately. So this was the response that we got from our users. Since I have some time, let me also try a risky thing and show a demo. So this is the Android app that we have built. It is a simple state machine that runs on the background, and this is the device that we have. Since I do not have Wi-Fi, I will keep the demo for the demo session. All right, so what is the summary? GesturePod is an easy-to-integrate device that clips onto any white cane and detects gestures performed with the cane. With GesturePod, users can perform common tasks on the smartphone without touch or even removing the phone from the pocket or bag. I should point out that the code for GesturePod, a simulation if you don't have the hardware, and the ML dataset has all been released under the MIT open source license, and you can access it there. And come see us at the demo to learn more. Thank you.
Thank you so much for the presentation. Any questions?
Really nice work.
Thank you.
It occurred to me that I would like to use this, but I don't have a cane. Is it? Did you consider like attaching it to the wrist or the finger or something?
Yeah, so that's a very good question. What we have exposed is a pipeline that enables you to do this. But we don't have a solution yet, as in we have a pipeline that you can do it, and we'll be happy to work with you. But as of now, we did it for a cane because we realized that most people use the cane. Any more questions?
A quick question. Here.
Yeah.
So when the user performs the interaction, do they have to stop, or they can keep walking and perform the interaction?
Yeah, that's a very good question, and I should point out P3. When we designed the gestures, we thought that they could momentarily stop for some time and then perform the gesture. That was how we designed it, but the users learned that they could perform the gesture while walking. You could keep walking, do a double tap, and continue to walk. Since I've connected to the Wi-Fi, let me actually show you the demo right now. So this is just a state machine on the app that keeps running in the background, and then you perform a simple task.
www.google.com, download error.
So that was the Wi-Fi error. It tells you that there is a download error, and then you can...
Maps, know before you go. Get updates if your commute is bad. From Bluetooth share, sent files, 1 successful, 0 unsuccessful.
So that was just...
Home.
And then we have state machine.
Current time is 11:35 p.m.
So you get the fact, right? It's a simple state machine that you can customize as well, and then you can perform different gestures, and we also have simple state machines that help you start, stop, or navigate between the different things. Yeah. Any more questions?
I have a question. I'm wondering how you came up with those 5 gestures. Did you
Right.
observe any visually impaired people or?
Yeah, so I didn't mention here, but we did a first round of participatory interviews, and these guys were not part of our user studies when we went and asked them, what are the problems that you face? What sort of gestures would you like? And most importantly, it was also motivated by the users' talk back on the Android. So people do this to go next, do this to go back, so you have a navigation. So we thought right twist and left twist is a good mapping for that. And then they have a home button as well. So most phones have a home button, so we thought double tap is like a home button. So it was partly motivated by Android Talkback and partly by what we spoke to the users. Yeah.
Thank you. Any other question? Okay, so let's thank our speaker again.
Thank you.